This is a film of lab number 6, which some people missed because of the Queen's birthday weekend. What I want to do is perform the lab for you and give you the results, and the people who missed it can write up their logbook from these results. So, you see the circuit for lab number 6 on page 27 of your orange book, and first up we have a coil, a capacitor and a resistance all in series. So I'm wiring it in series. You see, putting one after the other. Okay, now it's in series. And then we get the scope. Remember, the black wire on the scope must go to earth. That's the only place it's allowed to go. So I look at the earth terminal and I make sure I put the black to the right place. And the red one goes across the resistance. So you see the scope is measuring the voltage across the resistance. Now, we're going to go through a whole set of frequencies and measure what the result is. I'm going to gradually increase the frequency in steps and measure the voltage in each step. Now, the way we can do this is one of two ways. We can either use the peak-to-peak value, which is by just measuring peak-to-peak on the scope, or the scope also has the facility of measuring the RMS value. It's possible to read the RMS value directly from the scope. So either we look at the RMS value or you measure peak-to-peak. It doesn't make any difference as long as you keep to the same thing all the way through. Okay, so if I increase the frequency, watch what happens. That signal's going to get bigger. And then it starts to get smaller once we've gone through the resonant frequency. So I click it up and see it's smaller again. It gets bigger. Let's increase the gain so you see it more dramatically. So you see it gets bigger and then smaller as the frequency changes. Now this concept is known as resonance. What happens is the XL, which we've done in class, remember, 2 pi FL, and the XC, 1 over 2 pi FC, they both change with frequency. And there's always just one frequency where the XC equals the XL. And if that happens, we call it resonance. And in this lab, what we're doing is we're searching for that resonance point. And we're going to wire the circuit up first in series like that, and then we're going to change it to parallel, as you see in your book on page 27. So we take those results and we write them down in your logbook. Now if you look at the whiteboard, you'll see that we've got the results for you. And what you can do is you can pause the film and copy this down into your logbook. So you've got your results. What we did was we had a high resistance and in series. It's a series circuit, so the resistance was high. We measured VR and we saw the voltage increased and then decreased, just as it should according to resonance. Then we tried with a different resistance. First it was 1400 and it was 700. And again we got the same result, bigger and then smaller. Finally we had the two C and the XL in parallel. Now when that happens, it's different, because here, when you're at the resonance point, because you have XC times XL over XL plus XC, it means that we get 0 on the bottom line. XL times XC over XL plus XC. Now you see, if XL is equal to minus XC, that's going to go to 0. So your bottom line is 0, divided into a real number means you get infinity here. So you actually block the frequency at resonance, and that's what we see. Now with those results, you have to plot them out. Now the way you plot them is like this. In your logbook, you just do a sketch, and you do a graph of log frequency. You start at 100, and then you take individual steps, where decades equal steps, equal decade steps. So you see what's happening? I'm going 100 times 10 is 10 to the 3, 10 to the 4, 10 to the 5, and they're equal steps. Then a bit less than halfway is where you put the 2's. 2, 2, 2. And then that's going to be 200, that 2 is 2,000, and that 2 is 20,000. And you put the 5's halfway between there. 5, 5, 5. So that 5 is 500, that's 5,000, that's 50,000. So what you've done there is sketched a log curve. And then you plot you plot your readings on this curve, and what you'll find is that with the high resistance, with 1400, you see a curve like this. With the lower resistance, 700 in series, you'll see it like this. And with the parallel one, it'll be the other way around. It will dip rather than rise. So with a parallel circuit, you see a dip like this as you plot your graph. So you must put that graph into your logbook. And then, at the end of the lab, in the conclusions, it asks you for, it asks you to work out the calculated resonant frequency, because you know the value of L and C. I can tell you what they are. I've forgotten. 0.022 is the 120. Okay, so we've got L equals 120 millihenries, and C is 0.22 microfarads. So from those two numbers, you can use the formula in the book to calculate this resonant frequency, which actually comes around 2K, I think, if you plot it properly. Okay, now the other thing it talks about is Q. Q is the quality factor. The Q does not mean coulombs in this case. It means how good is your coil. And a coil that has a very sharp resonance, looking like this, that's considered to be a high Q. Now, it's pretty low Q in this lab, but you do see that the Q changes. It should be that you get a sharper curve for the low resistance and a shallow curve for the higher resistance. So that's high R res, let's say, and that's low res. Okay, so that is the lab number 6. Now, from what you've seen here, it should be possible for you to write up your log report. You don't worry about the signature on your report because we have no time to do that. One more thing I should mention, back looking at the results, I didn't bother doing these because I know it's not going to change. Once you get to the high frequencies, then the circuit's going to block to the same amount. So at high frequencies, this circuit is going to have the same voltage across there the whole time. Okay, so that is the lab number 6.